Performing an alignment. In this training module, we are going to dive deep into the alignment process. We will discuss alignment geometry, identify various positions of the wheel tire assembly, as well as steering and suspension components in relation to each other and to the vehicle. Performing four-wheel alignments is a complex skill that every automotive technician will need to master as they advance in their field. An alignment is generally performed every 12,000 miles or 12 months, whichever comes first. It's a safety-related maintenance that will help keep the vehicle safe on the road, improve handling performance, and help maximize tire life. Incorrect wheel alignment geometry can be the cause or contributing factor to nearly every type of handling and/or steering complaint. The inspection of wheel alignment geometry reveals not only adjustment errors, but also allows you to verify the condition of suspension and steering components. The primary geometric elements that consist of the vehicle's wheel alignment are as follows: camber, front and rear; caster, toe, front and rear; and thrust angle. First, we will discuss camber alignment. Camber is the inward or outward tilt of the top of the wheel tire assembly. This angle is formed by a vertical center line and tire center line. Positive camber describes the top of the tire tilting away from the vehicle, while negative camber describes when the top of the tire tilts inward toward the center of the vehicle. Zero camber is the point where the vertical and tire center line are the same. There are advantages to positive camber, such as reduced road shock, enhanced directional stability, and minimized tread wear. An advantage of negative camber is cornering performance. Camber spread or cross camber is the difference in camber values between the left and right side of the vehicle. For diagnosis of pulling complaints, remember camber values may be within specifications and still cause a complaint from excessive cross camber. The diagnostic rule is camber pulls positive, meaning the vehicle will pull in the direction of the wheel with most positive camber value. Rear wheel camber is generally specified as negative on the vehicles with independent rear suspension. A small amount of negative camber at the rear improves cornering performance by applying maximum tread to the road surface. Solid rear axle design operates with zero camber. Any significant camber or toe reading with this style of suspension may indicate bent or damaged componentry. Next, we'll discuss caster alignment. Caster describes the forward or rearward tilt of the steering axis compared to the vertical reference when viewed from the side. The caster angle is formed by the intersection of the steering axis and vertical line through the wheel center line. The steering axis is an imaginary line that the spindle pivots around. On a double wishbone suspension, the steering axis is a line extended through the upper and lower ball joints. The pivot points to the spindle. On a McPherson strut suspension, the upper strut bearing and lower ball joint define the steering axis. Caster is designed into the front suspension geometry of a vehicle for two reasons: directional control and steering returnability. A vehicle's weight or load is projected down through the steering axis to the point where the steering axis meets the roadway. By tilting the steering axis rearward or positive caster, the point of load or weight of the vehicle extends ahead of the tire's contact patch. The distance between the tire's contact patch and the point of maximum load is known as caster trail or lead. Caster trail or lead causes the front tires to follow the weight of the vehicle. Let's review bicycle steering as an example. Bicycles typically use a significant amount of positive caster. The caster trail is large as the point of load projects far ahead of the tire's contact patch. Do you recall how easy it is to ride a bike without using handlebars? You were able to steer the bike hands-free because the front tire followed your weight due to positive caster trail. Now imagine turning the handlebars backwards and try to ride without using your hands. The caster angle is now negative, and the point of load follows the tire's contact patch, providing no stability and extremely poor directional control. In other words, the weight or load is pushing the wheel forward instead of the load pulling the wheel. Two significant drawbacks to large caster trails are increased steering effort and increased road shock. Caster's influence on directional control is significant, providing both the steering returnability and directional stability. A difference in caster between the left and right side of the vehicle will induce a pulling condition. This difference in caster is described as cross caster. A vehicle will pull or drift toward the side of the vehicle with the least amount of positive caster. The diagnostic rule regarding cross caster is caster pulls negative. As the caster angle increases toward positive, a greater lateral force is applied to the wheel assembly and steering linkage. A difference in caster values between left and right sides of the vehicle allow the side with more positive caster to push the vehicle toward the side with the least amount of caster. In recent years, some manufacturers have designed vehicle suspensions to take advantage of the virtues of high positive caster without dramatic increases in steering effort and road shock. This is effectively known as Vorloff geometry. By offsetting the steering axis rearward of the wheel center line, the caster angle can be increased without greatly increasing the caster trail. On conventional front suspension design, the steering axis intersects the wheel center line. Consequently, any increase in caster provides a proportional increase in caster trail. Knock-Loff geometry offsets the steering axis ahead of the front wheel center line. This arrangement increases the caster trail without a corresponding increase in caster angle. This provides improved directional control without a large amount of camber roll. A caster value deviating from spec can have several causes. Caster error at both front wheels can often be traced to the relationship between caster and the level of the vehicle. By raising the rear of the vehicle, caster shifts to negative, and by lowering the rear of the vehicle, as in sagging springs or overload conditions, caster shifts to positive. Large individual caster errors suggest possible bent or overworn suspension components or even structural damage. Now, we will review toe alignment. Toe is the difference in the distance between the front of the tire and the rear of the tire when viewed from above. Toe describes the angle formed by the vehicle's center line and a line extended through the center of the tires. Toe in results when the front tires point inward when viewed from above, and is also referred to as positive toe. Excessive toe in causes a condition where each wheel individually attempts to align itself straight forward. As each wheel aligns itself straight ahead, the opposite wheel assumes all the toe value. As the wheels alternate between straight and toe in positions, the steering linkage and steering wheel oscillate back and forth, creating a shimmy. Toe out results when the front tires point outward when viewed from above and is also referred to as negative toe. With excessive toe out, each wheel will roll in opposite directions and neither can find a straight position. When the two front wheels are pointing in opposite directions, the vehicle wanders and requires constant steering input to keep traveling straight forward. Zero toe occurs when angles from the front tires are the same distance apart when measured from front to rear of the tire. Toe can also be described as total toe or individual toe. Individual toe refers to a single wheel compared to the vehicle's center line. Total toe describes the sum of individual toe values. The sum of left toe plus right toe equals total toe. Total toe and individual toe are defined as the same when applied to both rear and front wheels of the vehicle. Toe in or positive toe is applied to the rear wheels of independent rear suspension vehicles to improve both cornering performance and straight line stability. As tire profiles have decreased with shorter sidewalls and wider tread, suspension bushing compliance has increased to maintain acceptable ride quality. This compliance, when excessive, can produce negative influences on vehicle handling. The positioning of the rear wheels also determines the straight ahead position of the front wheels. While the front wheels provide the steering for the vehicle, it is the rear wheels that determine the direction the vehicle will travel. If the rear individual toe values are equal, the front and rear wheels will both be parallel to the vehicle's center line while traveling straight ahead. Toe out at the rear is the source of most rear suspension handling complaints. Negative toe may cause the vehicle to wander at the rear when traveling straight ahead. When turning, excess rear toe out may also cause an oversteer condition. A static toe in setting prevents the situation by providing understeer, which delivers stable handling for the average driver. Lastly, we will review thrust alignment. The thrust line is the average direction of the rear wheels. The thrust line divides or bisects the vehicle's rear total toe value. The intersection of the vehicle's geometric center line and the thrust line form the thrust angle. Remember, the geometric center line is simply a line extending through the midpoint of both the front and rear axles. When the thrust line extends to the left of the geometric center line, the thrust angle is negative. The rear wheels of the vehicle are pointed to the left. A positive thrust angle describes the thrust line extending to the right of the geometric center line. The rear wheels are then pointing to the right. Now that we have reviewed alignment geometry, we will review the 12 main steps of performing a four-wheel thrust alignment. 1. Equalize all tire pressures to recommended limits, then perform a test drive. 2. During test drive, note where steering wheel clocking is when tracking straight or close to straight. 3. Determine direction of pull and push, and note how vehicle tracks. Is it crab walking, wandering, shimmying. 4. Position vehicle on alignment rack with front wheels centered on turntables. Leave pins in turntables front and rear. 5. Raise the vehicle and inspect for damage, bent suspension, or steering components. If damage identified, notify advisor that the damaged components need to be repaired before performing alignment. 6. If no damage found or after damage repaired, log into alignment machine and enter logistics, RO number, customer name, last 8 of VIN, vehicle selection. 7. Mount aligner heads and compensate. Install brake rod, pull front and rear turntable locking pins, then perform caster sweep. Note, this is not optional. 8. Center and lock steering wheel, store before alignment readings, check aligner menu. 9. Set rear camber, then set rear toe. This also sets the thrust line. Jounce rear end and confirm adjustment hold. 10. Jounce front end and then make camber and caster corrections. Cradle shifting may be needed to complete. 11. Adjust front toe. Jounce front end between adjustments. If necessary, shake out. Finalized alignment is accomplished when jouncing front end and toe steer head settings return to the same spots. Ensure adjustment locks are tightened before jounce. 12. If thrust line remains true at 0 and front toe settings stay where set, alignment is complete. Then print 2 copies of before alignment readings and 2 copies of completed alignment. 1 copy of each before and after printout is for the customer. The other copies remain with repair order for record keeping. Note, heating of jam nuts and eccentrics will cause swelling and steering linkage. Be aware this will change your toe rating noticeably. You must cool the assembly to obtain correct readings. Also, reinitialize or relearn EPS system if vehicle equipped with this system. Generally, every 12,000 miles or every 12 months, whichever comes first, a vehicle needs to be aligned. This is because the steering and suspension systems relax and settle out of alignment, which can cause damage to these components and the tires if not corrected. Alignments help keep the vehicle steering and suspension components performing as intended and helps extend the life of the tires, which saves the customer money in the long run. Always follow your manufacturer's specific guidelines for performing all maintenance, and during the MPI, identify and document any damage or maintenance requirements, such as 4-wheel alignments, to help keep the vehicles you service safe and operating at maximum performance. It's quiz time! Please take the Performing and Alignment Comprehensive Quiz.